Before we touch calculus, we need absolute clarity on one idea: the function. Look around you. The world is saturated with relationships between quantities. A ball rolls across the floor. The longer it rolls, the farther it travels. Time and distance, related. Money sits in a bank account. Each year, the interest compounds. Time and money, related. Climb a mountain. The higher you go, the colder it gets. Altitude and temperature, related. The national debt rises and falls with political decisions. Time and debt, related. Each of these is what mathematicians call a function, a relation between variables. But this definition is too loose for calculus. We need precision. Not every relationship qualifies as a function for calculus. Consider this statement: a person's obligation to society increases with age. This is a relationship. Obligation and age are related. But can you measure obligation? Can you assign it a number? No. Obligation is not numerically measurable. Calculus cannot work with it. Now consider, the distance a dropped ball falls depends on how long it's been falling. Time, measurable in seconds. Distance, measurable in feet. Both are numbers. This is a function calculus can handle. The calculus is concerned only with variables whose values can be expressed numerically. Time, distance, money, temperature, pressure, velocity. All measurable, all fair game. Let's get concrete. Here's a ball held still. The instant I release it, a clock starts. As time passes, the ball falls. Watch. After 1 second, 16 feet. After 2 seconds, 64 feet. After 3 seconds, 144 feet. Notice something. The distance isn't just increasing, it's increasing faster and faster. In the first second, 16 feet. In the second second, 48 more feet. In the third second, 80 more feet. This isn't linear growth. This is acceleration. There's a precise pattern here. What's the pattern? Look, 16 equals 16 times 1, and 64 equals 16 times 4, and 144 equals 16 times 9. The distance equals 16 times the square of the time. S equals 16 times t squared. This formula is extraordinary. 5 symbols capture an infinite relationship. Give me any value of t, and I can tell you exactly how far the ball has fallen. When t equals 2.5 seconds, s equals 100 feet. The formula knows. The formula is mathematics' sharpest representation of a function. It's compact, it's complete, it's computable. Let's look more carefully at this formula. I choose a value for t. That choice determines s. I don't choose s. It's forced by my choice of t. We call t the independent variable. I'm free to choose it. And s is the dependent variable. It depends on t. But here's something subtle. I can solve for t instead. If s equals 64, then t squared equals 4, so t equals plus 2 or minus 2.
Wait, 2 answers? When I input s equals 64, I get 2 possible values of t. That's a problem. Calculus works with single-valued functions. One input gives exactly one output. So we treat these as 2 separate functions. T equals the positive square root of s over 16. T equals the negative square root of s over 16. Physically, only the positive one makes sense. Time doesn't run backward. This is why we write s equals 16t squared with s alone on one side. The formula shows which variable is determined by which. There's another way to see a function, as a picture. In the 17th century, René Descartes and Pierre de Fermat invented coordinate geometry, a way to turn formulas into curves. The idea is simple but profound. Each pair of related values, each t with its corresponding s, becomes a point in the plane. When t equals 0, s equals 0. That's the point 0, 0, the origin. When t equals 1, s equals 16. That's the point 1, 16. When t equals 2, s equals 64. When t equals 3, s equals 144. Now connect them with a smooth curve. This curve is called a parabola. Every single point on this curve represents a moment in time and the distance fallen at that moment. The curve contains infinite information, every possible t value, every possible s value, all visible at once. But I must warn you about something. This curve is not a picture of the motion. The ball falls straight down. The parabola curves sideways.
The curve is a picture of the relationship, how distance relates to time, not a picture of the path. And there's more. Physically, the ball might hit the ground after 5 seconds. The actual motion stops. But the mathematical curve extends forever. -t, t equals 100, any value. The formula and the curve are mathematical objects. They have meaning beyond the physical situation that inspired them. Not every function is as well behaved as s equals 16t squared. Consider this function, y equals 1 divided by x minus 2. What happens when x equals 2? The denominator becomes 0, and division by 0 is not defined. It's meaningless. There is no value of y when x equals 2. Look at the graph. The curve approaches x equals 2 from both sides, but never touches it. There's a hole, a missing point. This function exists for every value of x except 2. The collection of x values where the function is defined is called the domain. For this function, the domain is all real numbers except 2. Here's another example. Y equals the square root of 1 minus x. What if x equals 5? The square root of -4. That's not a real number, it's complex. In this course, we stick to real numbers, so x cannot be greater than 1. The domain here is all x less than or equal to 1. The concept of function does not require a y value for every x. It requires a y value for every x in some specified domain. Now let me show you something that seems like nothing, but is actually everything. Consider this function. Y equals x squared minus 4 divided by x minus 2. We can factor the numerator. X squared minus 4 equals x plus 2 times x minus 2. Now it's tempting to cancel. But wait, what did we actually do? We divided numerator and denominator by x minus 2. Division by x minus 2 is valid unless x equals 2. When x equals 2, we divided by 0. So the simplified function y equals x plus 2 is not the same as the original. The original function has no value at x equals 2, but the simplified version does. It equals 4. Here's the profound observation. Even though the original function has no value at x equals 2, as x gets closer and closer to 2, y gets closer and closer to 4. From both sides, closer and closer. Never reaching, but always approaching.
We say the limit of y as x approaches 2 is 4. The function never equals 4 at x equals 2, but it approaches 4 as x approaches 2. A function may approach a limit at a value where the function itself does not exist. This idea that a function can approach a value it never reaches is the seed of calculus. We will return to it. It is everything. One practical matter before we close. We'll be working with many functions. Writing them out repeatedly is tedious. Mathematicians invented a shorthand, function notation. We write f of x to name a function. The letter f is the function's name. The x in parentheses is the input variable. So if f of x equals x squared minus 9, then f is a rule. Take the input, square it, subtract 9. What is f of 3? F of 3 equals 0. What is f of -2? F of -2 equals -5. When we have multiple functions, we use different letters. F for one, g for another. F of 5 equals 16. G of 5 equals 2. No confusion. One warning, f of x does not mean f times x. The notation must be taken as a whole. Let's crystallize what we've learned. A function is a relation between numerically measurable variables. A formula expresses that relation precisely and compactly. A graph visualizes that relation as a curve. The domain is the set of inputs where the function is defined. A function can approach a value at a point where it doesn't exist. From now on, when you see a function, ask, what is the domain? What happens at the boundaries? Next time, we use functions to ask a deceptively simple question. If a ball is falling, what is its speed at a single instant? The answer will be 0 divided by 0, meaningless. And from that impossibility, calculus is born. Thanks for watching. Subscribe so you don't miss the next episode.